Hi everyone. Now we will read about the properties of the autocorrelation function. Okay. So whenever we are going for the properties of the autocorrelation function, first we need to consider our random process x of t. So we are considering a random process x of t is at least wide sense stationary. At least the wide sense stationary WSS random process. Meaning that WSS random process x of, so the autocorrelation function, that is Rxx of t comma t plus tau, is function of tau, is function of tau only, that is the time difference. So we can write this as Rxx of tau. So we are assuming, before writing the properties of the autocorrelation function, we are assuming that the random process x of t is at least wide sense stationary random process, meaning that the autocorrelation function Rxx of t comma t plus tau is function of tau only, that is the time difference between t2 minus t1. Okay, so that is we are writing always our autocorrelation function as Rxx of tau. Before writing the properties of the autocorrelation function, you must write this sentence. We are assuming that our random process is WSS random process, then only the following properties are applicable. Okay, so don't go for the properties directly before writing this. First write this sentence, then go for the properties. So the first property of the autocorrelation function is the mean square value of x of t. Mean square value of x of t. So mean means how we are writing e of x of t. Mean is always represented as expected value. Mean square means e of x square of t is equal to the autocorrelation function at tau is equal to 0. That is Rxx of tau at tau is equal to 0. That is nothing but Rxx of 0. This is the first property of the autocorrelation function. Mean square value of x of t can be calculated as by substituting the tau is equal to 0 at autocorrelation function. Now we will see the proof of this one. How will you prove this one? First, we know that the per random process x of t, the autocorrelation function can be written as Rxx of tau is equal to e of x of t plus tau. Okay, this is the formula for the autocorrelation function. So you remember what the students are doing mistake is, whenever they are writing the random process, always you have to write the capital X here. Okay, so these are the brackets, and whenever you are writing expected value, you need to write these brackets. Okay, so E of always the random process should be in capital letters. E of x of t plus tau. So if you remember, whenever we are doing for the random variables, the correlation between the two random variables x and y, we are writing it as rxy. Rxy is equal to E of x y. If you remember in the whenever you are studying the multiple random variables, the if you remember this formula, then you can write directly. So always the formulas are linked between the previous one. Okay, so the autocorrelation function Rxx of tau is equal to E of x of t plus tau. Now what we are doing is substitute tau is equal to 0. So what we'll get? Rxx of 0 is equal to, just in place of tau we are substituting 0. E of x of t. If I substitute here tau is equal to 0, E of x of t. So what we will get? E of x of t into x of t, x square of t. Okay, so Rx of 0 is equal to E of x square of t. That is, the mean square value can be calculated as by substituting the tau is equal to 0 in the autocorrelation function. That's all. This is the proof for the first property. Then we'll go for the second property. First, always whenever they are asking a question, write about any state and prove any 4 properties of the autocorrelation function or 5 properties of the autocorrelation function. So first I will list the very easy properties for you. Okay? So the second property is autocorrelation function is even function. Okay, so autocorrelation function is even function. Okay, so if you remember, when we can say a function is an even function, when x of t is equal to x of minus t, then we can say that function is an even function. Now we are saying autocorrelation function is an even function. So autocorrelation is Rx of tau. What we write? Rx of tau is equal to Rx of minus tau. That's all the equation. So if you remember this condition for even function, the function replace t, the variable, with the minus variable. So here the variable is tau. Then replacing Rx of tau is equal to Rx of minus tau. This is one of the properties. So the autocorrelation function is an even function. How will you prove this one? So as we always write, we know that Rx of tau is equal to E of x of t, x of t plus tau. Okay. Now what we are doing is substitute tau is equal to minus tau. So we write this formula. Now we are going for this one. What will we get? Rx of minus tau is equal to, in this equation. In this equation, just a substitute tau is equal to minus tau. E of x of t. What will get here? X of t minus tau. Okay. Now what we'll do is let this t minus tau as another variable, some u. You can use any variable. Just we are assuming that u. Okay. So now what will happen to t? T is equal to this tau. If you go that side, u plus tau. Okay. So substitute these values in that above equation. What will get? Rx of minus tau is equal to E of, what is t? T is equal to u plus tau. Sorry, x of u plus tau. X of t minus tau is u. Okay. So that is equal to, so u is in any another variable. You can replace u with t. Okay, no problem. X of t, x of t plus tau. That is nothing but Rx of tau. Okay. So here Rx of minus tau is equal to Rx of tau. So autocorrelation function as even function. Okay. Just you are writing the formula, substituting tau is equal to minus tau. Then we are assuming t minus tau is equal to u, and then we are doing that substitution. That's all. So this is the second property. Now we'll go for the third property. Okay. So autocorrelation function. The third property is autocorrelation function. If x of t is periodic, meaning that random process is periodic. If x of t is periodic, then autocorrelation function is also periodic. Then autocorrelation function, that is Rx of tau, is also periodic. Is also periodic. Okay. Now we'll go for the proof. If you remember, when we can say a signal is periodic, if x of t is equal to x of t plus capital T, where t is the time period. Okay. So you can replace t or t naught, whatever you want. Okay. Now we are assuming that x of t is periodic. Okay. So x of t is periodic. Then what is the condition we need to write? X of t is equal to x of plus or minus. Okay. X of t plus or minus t plus tau is equal to x of t plus tau plus or minus t naught. So in place of t, we are writing t plus tau. So periodic means if you see this is sinusoidal signal is in periodic. I write like this. Okay. So whatever the value here, the same value is here. Meaning that if I take this pi, 0 pi, 2 pi, 3 pi, 4 pi and 5 pi. Okay. So this is 4 pi. Okay. Time period. So t plus pi. Whatever we are having at the value pi, the same value is at 5 pi. Okay. So that's why we are writing t plus t naught. X of t plus tau is equal to x of t plus tau plus or minus t naught. Now, what do we need to prove? Our x of tau is also periodic. So what will write first the formula for our x of tau? We know that. So what is the formula? E of x of t, x of t plus tau. Okay. So this is the formula. Now, what we need to show is also periodic. Rxx of tau is equal to Rxx of tau plus or minus t naught. That is the condition. So we will take Rxx of tau plus or minus t naught. That is equal to, so E of, in place of tau we are writing tau plus or minus t naught. So E of x of t, x of t plus, in place of tau what we are having? Tau plus or minus t naught. Okay. So that is equal to E of x of t. Okay. So if you see here, x of t plus tau plus or minus t naught is equal to x of t plus tau. Okay. From that one. So what is this one? E of x of t plus tau. That is nothing but Rxx of tau. Now you see Rxx of tau plus or minus tau naught is equal to Rxx of tau. So we show that Rxx of tau, that is autocorrelation function, is also periodic. Therefore, Rxx of tau plus or minus t naught is equal to Rxx of tau. Therefore, autocorrelation function, right? Therefore, autocorrelation function is also periodic. Okay. Next, we will go for the fourth problem. If a random process x of t, okay, so we are having a random process x of t, and we are having a DC component A, okay, and we are assuming that another random process y of t is equal to a plus x of t. A is a DC component and x of t is a random process. A is a DC component. We are defining another random process y of t is equal to a plus x of t. Then Ryy of tau, that is the autocorrelation function of random process y of t, is equal to a square plus Rxx of tau. Rxx of tau is the autocorrelation function of x of t. Ryy of tau is equal to a square plus r. Now we'll go for the proof of this one, meaning that we are having a random process x of t. We are adding a DC component to the random process x of t. What is the autocorrelation function of that addition of the random process x of t and the DC component? Okay. So if you see, whenever we are going for any communication system, we are having a random signal x of t and we are transmitting through channel. If a particular noise is adding to that signal, that is a constant. If you say a constant noise, then what is autocorrelation function at the receiver side? Okay. So if you know the signal and the constant, you can calculate the autocorrelation function at the receiver by using this formula. Okay. That is one of the applications. How will you prove this one? So first method, they had given y of t is equal to a plus x of t. Okay. So what is Ryy of tau? That is the autocorrelation function of y of t. That is equal to expected value of y of t, y of t plus tau. Okay. That is the formula. That is equal to expected value of what is the value of y of t, a plus x of t, okay, into y of t plus tau means in place of t substitute t plus tau, that is a plus x of t plus tau. Okay, so that is equal to e of, multiply those two, a into a, first a square plus a into x of t, a x of t plus next a into x of t plus tau plus x of t into x of t plus tau. Just a plus b into c plus d formula. Just multiply those two. Okay, that is equal to. Now, if you remember the properties of the expectation can be applied for individual functions separately. Okay, now e of a square plus e of a x of t plus e of a x of t plus tau plus e of x of t plus tau. Okay, now if you remember once again the properties of the expectation, a is a constant here. DC component means a is constant. So if you remember, expected value of constant is equal to the constant. That is one of the property of the expectation. So e of a square is equal to a square because a is constant, a square is also constant. Expected value of constant is constant. Plus, if you remember one of the next property, e of ax is equal to a into e of x, where a is a constant. Okay, a is a constant. So here a is a constant. So you can take outside of the expectation a into e of x of t plus a into e of x of t plus tau plus e of x of t plus tau. Okay, now here we're assuming that the mean of the random process is equal to the 0. That is mean e of x of t is equal to the 0. So this becomes 0 and this is also mean, whatever the mean value either x of t or t plus or whatever the variable. So this becomes 0, this becomes 0. Then what is the remaining thing we are having? That is equal to a square plus e of x of t x of t plus tau. So that is nothing but a square plus rxx of tau. So ryy of tau is equal to a square plus rxx of tau. Okay, this is one of the property. Next, we will say another property. I think fifth property. Okay. Previously, y of t is equal to a plus x of t. Now we consider z of t. Z of t is equal to x of t plus y of t. Okay. So another, we are taking the sum of the two random processes. That is x of t is a random process, y of t is a random process, z of t is also a random process. Z of t is taken as the sum of the two random processes, x of t and y of t. Then, if you calculate the autocorrelation function of z, that can be written as rxx of tau plus rxy of tau plus ryx of tau plus ryy of first xx, that is the autocorrelation function of x plus cross correlation function of x and y, cross correlation function of y and x, and the autocorrelation function of y. Now same proof, whatever we have done previously, same procedure. So e of z of t, that is r z of tau is equal to e of z of t, z of t plus tau. Okay, so that is in place of z of t, substitute x of t plus y of t. In place of z of t plus tau, we need to write x of t plus tau plus y of t plus tau. Okay, that is equal to, just multiply e of first x of t plus tau, next plus x of t y of t plus tau plus next this one y of t x of t plus tau plus y of t plus tau. Now write the expectation separately. E of x of t plus tau plus E of x of t y of t plus tau plus E of y of t x of t plus tau plus E of y of t plus tau. That is equal to, what is the first formula? X of t plus tau, that is Rx x of tau plus, what is this one? R x y of tau. First we are having x, then y. Yes. Next we are having first y, then x. So R y x of tau plus y y. Both are y's. R y y of tau. See, very simple. Only we are writing the formula autocorrelation. Just multiplying and again writing. So this is one of the property of the autocorrelation function. Okay. So whenever they ask the properties of the autocorrelation function, you can write these 5 properties. And then okay. Okay. Then I will tell one more property which is used for solving the problems. Okay. That is another property where you can use this property as a problem solution. Okay. So the last property. We are assuming that a random process x of t has non-zero mean value, meaning that e of x of t is not equal to 0. X of t has non-zero mean value, non-zero mean value, that is e of x of t is not equal to 0, and ergodic with no periodic components, and ergodic with no periodic components. So that's why we told this property is somewhat difficult. Why the students need to write entire x of t is non-zero mean value and ergodic with no periodic components. Then limit tau tends to infinity, or x of tau is equal to x bar square. Meaning that when the autocorrelation function tau, the value, that function value tau tends to infinity, then that is equal to the mean. X bar is nothing but the mean of the random process x of t. That is called the mean, square of the mean value. Okay. Don't say that mean square is different from square of the mean. Mean square is x of e of x square of t. That is mean square value. Now this is mean square of the mean. Square of the mean. This is mean square value. Mean square value. This is square of the mean. Okay. So this is the statement. Now we'll go for the proof. Okay. So we are considering that x of t is a random process and it has no periodic ergodic with no periodic components. Then limit t tends to infinity, or x of tau is equal to x bar of t. Okay. Now consider the random process x of t with 2 random variables, x of t1 and x of t2. Okay. Then autocorrelation function or x of tau can be written as e of x of t1, x of t2. Okay. Since the process has no periodic components, as tau tends to infinity, what is the meaning that when no periodic components means then the random variables become independent. So we can write this as e of x of t1. Independence means e of x is equal to e of x into e of y. So x of t1 into e of x of t2. Okay. So when no periodic components as tau tends to infinity, then the random variables x of t1 and x of t2 becomes independent. When the two random variables are independent, we can say that e of xy is equal to e of x into e of y. Okay. Now we told that ergodic. Ergodic means the mean value, that is the e of x of t can be written as x bar. This is also equal to x bar, whatever it may be the random variable t1 or t2. So x bar into x bar can be written as x bar square. Therefore, The mean value, whenever in the problems they will give the autocorrelation function, they will ask you to calculate the mean value. So if ask you to calculate the mean value, then substitute tau tends to infinity in the autocorrelation function, then we can get the mean value. So for proving it well, the statement is x of t, it is not having the mean value is not equal to 0 and it is ergodic with no periodic components. So no periodic components, then we can say that it is independent. So with this no periodic components, we are writing e of x is equal to e of x into e of y. It is ergodic. So we are writing e of x of t as x bar and x of t2 is x bar. So it is equal to x bar square. So this is about the properties of the autocorrelation function. Thank you.